In today's lecture, we will learn some properties of vector space. First, we will show 0 dot x equal to 0, where 0 is a member of field and x is an element of vector space V. So 0 plus 0 when applied on x, this gives you 0 dot x plus 0 dot x. This holds due to distributive property. Next, 0 plus 0, actually gives you 0. That is, in vector space V, 0 plus 0 is 0. This gives you 0, and here 0 dot x plus 0 dot x. Next, this 0 can be written as 0 plus 0x. We write this by using the property of the identity element. When identity element is added in element, then this element remains same. So we can write u as a 0 plus u. Similarly, we write 0x as 0 plus 0x. Now using the right cancellation law, we get 0 equal to 0x. That is by cancellation law. Using cancellation law, we get 0 equal to 0x. So this is the first property. That means when 0 is applied on x, we get 0. Remember, this 0 belongs to field, but when this is operated on an element of vector space, we get 0, and this 0 belongs to vector space V. So this is a vector element and this is a field element. Next, we will show alpha dot 0 equal to 0. We may use this property 0 plus 0 equal to 0 when alpha is operated on this equality. We get this, and by using distributive law, we get alpha dot 0. Alpha dot 0 gives you alpha 0. Again, making use of identity property, alpha 0 can be written as alpha 0 plus 0. And again, making use of the cancellation law, we get alpha 0 equal to 0. Here I am using identity property. And here we make use of cancellation law. So we get alpha 0 equal to 0. Remember, in this identity, alpha is a member of field and this is a vector 0, and again this 0 is again belongs to vector. So when a scalar operated on 0 vector, we again get a 0 vector. Next property is third one, minus alpha x equal to minus alpha x is equal to alpha minus x. Here first we prove this and then this one. So how to prove this? Minus alpha x equal to minus alpha x. Remember, if u belongs to V, that is, if u is a vector element, then minus u represent inverse of u. And what is the relation between u and inverse? When u is added with minus u, we get the identity element 0. We make use of this property here. Here minus alpha x means the inverse of alpha x. So inverse of alpha x is minus alpha x. So when we add alpha x plus its inverse is minus alpha x. Then if we get 0, it means minus alpha x is inverse of alpha x. So let us see what happened. Here we again make use of distribution property. This is equal to minus alpha plus minus alpha into x, and this is a scalar quantity alpha and this is minus alpha. Then by the property of the field, alpha plus minus alpha gives you 0 into x. Here this 0 belongs to field, member of field, and x belongs to vector space. So their product is 0, that is a vector quantity. So this 0 here belongs to vector space V. So alpha x, when added into minus alpha x, we get an identity element. It means minus alpha x is an inverse of alpha x. That means minus of alpha x is equal to minus alpha x. Similarly, next we show that minus alpha x equal to, again we add alpha x and alpha dot minus x. Again making use of distribution law, that is scalar distribute over vector. So x plus minus x. Again by the property of the inverse, or here we are using the property in vector space V. So alpha x plus minus x gives you the 0, the identity element. Now alpha dot 0 is 0. Again this 0 belongs to vector and this 0 belongs to field, but their product is 0, that belongs to vector space V. So alpha x operated on minus alpha minus x, we get an identity element. It means inverse of alpha x is alpha minus x. That means minus alpha x is equal to alpha minus x. Next property is the third one. Next, fourth property, A or alpha operated on u minus v gives you au minus av. It is again very simple because we make use of distribution law here. So when alpha is operated on u minus v, it means alpha is operated on u plus minus v. Actually, what is minus of v? Minus of v is minus 1 into v here. So u minus v means u plus minus v. Now we operate alpha using distributive law. Alpha u plus alpha operated on minus v, and when alpha is operated on minus v, we get alpha operated on minus 1v, and it means alpha dot minus 1 into v, or this gives you minus alpha v here, or this may we write minus alpha v. So alpha u or this may be written as minus alpha v here. So we easily obtain when alpha is operated on u minus v, we get alpha u minus alpha v. So next property is a dot u equal to 0. If a is not equal to 0, then this implies u equal to 0. It is very simple. A belongs to field F. So by the property of field, because A is not 0, that is every non-zero element has an inverse, A inverse belongs to F. So AU equal to 0 implies when A inverse is operated on AU on both sides, we have A inverse AU is equal to A inverse 0, and using the associative property here, and A inverse operated on 0 gives you 0 vector, and this when A inverse is operated on A, then we get a multiplicative identity in field. So 1 dot u is equal to 0. This gives u is equal to 0. So AU equal to 0, and if A is non-zero element, then u became 0. In the next property, if AU equal to AV and A is not 0, then this implies u equal to v. Again we make use of the same property of the inverse here, because A is a non-zero element of field F. So A inverse exists in F. So apply A inverse on both sides of this identity AU equal AV, we get this. Now making use of the associative property, we get 1 dot u is equal to 1 dot v, and this gives you u equal to v. So by applying A inverse on the both sides of this identity AU equal to AV, we get this, and this implies 1 dot u equal to 1v, and finally we get u equal to v. Next property, we will prove alpha dot x equals 0 implies alpha not equal to 0 or x not equal to 0. That is, if this product of a scalar quantity and vector quantity is 0, then either one of them is 0. On the contrary, suppose that neither alpha equal to 0 nor x equal to 0. So since alpha is not equal to 0, alpha inverse exists in F, in field F. So applying alpha inverse of the both side of this identity, we get this, and it means alpha 0 applied on alpha using the associative property, and here alpha inverse operated on 0 gives you 0, and again this 0 is a vector quantity, and alpha not 1 alpha Alpha inverse operated on alpha gives the identity element 1 in field 1 dot x equal to 0 and 1 dot x is x, so x is equal to 0. But this is contradiction. Contradiction to the fact that x is not equal to 0. So our assumption is wrong. So either alpha is 0 or x is 0. So these are the properties. These properties may be proved by using some other methods. Maybe not necessarily these properties are proved in the similar manner. You make use of any properties and prove these identities. Okay. Next we prove cancellation laws. First one is u plus v equal to u plus w implies v equal to w. So we start u plus v is equal to u plus w because u belongs to vector space v, so minus u is also belongs to v. So we operate minus u on both sides of this identity. We add minus u on both sides. Now using the associative law, minus u plus v gives you minus u plus w. This. When u is added in minus u means it's inverse, we get identity element. So 0 plus v gives you 0 plus w. By this property, minus u added in u, we get identity element. That is the identity property. And here I am using the associative property. So this 0 plus v, when identity element added in v, we get v, and again when identity element is added in w, we get w. So this u plus v equal u plus w implies v equal to w. So this is the cancellation law and it is called the left cancellation law. Again next, in the similar manner, we may use another law, that is v plus u gives you w plus u implies v equal to w. By applying the similar method, that is by adding additive inverse of u on both sides and then applying the associative property, we get the identity element, and this gives us v equal to w. Next we will prove that identity element in V is unique. So 0 is the identity element. We need to prove that 0 is unique element of V. Suppose this is not the only element which act as an identity element. Suppose 0 dash is the another element which act as an identity element. Since 0 is the identity element, we get 0 plus V is equal to V for all V belongs to vector space V. Again 0 dash is the identity element. So 0 dash plus V again gives V for all V belongs to vector space V. Since V is equal to this and again V is equal to this, so equating these two elements, we get 0 plus V gives you 0 dash plus V, and again using the cancellation law, this gives us V, this gives us 0 equal to 0 dash using cancellation law. So identity element is unique in V. In the similar manner, we prove that the inverse element is also unique. Suppose V belongs to V and minus V is the inverse of V. Since minus V is the inverse of V, so V added in minus V gives us the identity element 0. This is, suppose this is first equation. Suppose W is another inverse of V. So W plus V gives us 0, the identity element. Or you may write, because of the commutative property, you may write V plus W equal to 0. From 1 and 2 we get V plus W equal to V plus minus V. And making use of cancellation law, we get W equal to minus V. So this implies identity is inverse. Like identity is unique in V, inverse is unique in V. That is, each element in V has a unique inverse.